check the telescope one more time. The sky is quiet, almost too quiet. Then you notice it. A faint point of light, drifting where nothing should be. Not blinking, not fading, just moving. Slowly at first, then faster. Cutting through the constellation like silk. This isn't an asteroid, and it isn't a comet. It's something far older. Something that has been travelling through the darkness between stars, long before Earth ever existed. Astronomers now call it 3I-ATLAS. An interstellar visitor. Right now, it's falling toward our Sun, and in just a few days, it will reach the closest point it has ever been to a star. No one knows what will happen next. The discovery didn't happen in some high-tech NASA facility. It happened on March 13th, 2024, when the ATLAS survey telescope in Hawaii, a system designed to hunt for potentially dangerous asteroids, caught something unusual. A moving speck of light, catalogued as C2024E5, appeared in the data. At first, astronomers thought it was just another comet. They see dozens every year. But within 72 hours, something didn't add up. The object's trajectory was wrong way wrong. Dr. Larry Deneau from the University of Hawaii's Institute for Astronomy was the first to notice. The orbital calculations kept failing, he later told reporters. Every time we plugged in the numbers, the computer spat back an eccentricity value above 1.0. That's not supposed to happen with solar system objects. You see, everything born in our solar system, every planet, asteroid and comet, follows an elliptical orbit around the Sun with an eccentricity below 1.0. It's a fundamental rule of celestial mechanics. But 3I/ATLAS, its eccentricity measured 1.03. That single number changed everything. It meant this object wasn't orbiting the Sun at all. It was passing through. Think about that for a second. This chunk of rock and ice originated somewhere beyond our solar system, travelled through the mind-bending emptiness of interstellar space, and just happened to wander into our cosmic neighbourhood. The odds of witnessing this are astronomically small, literally. Current estimates suggest only one or two interstellar objects larger than 100 metres cross through the inner solar system every year, and we're lucky to spot even one per decade. Within days, observatories worldwide swung into action. The Gemini South Telescope in Chile captured the first detailed spectra on March 18th. What they found was bizarre. The object was glowing with an unusual reddish-orange hue, and spectroscopic analysis revealed something unexpected: massive amounts of carbon dioxide, CO2, vaporizing from its surface. Not water ice, which dominates most comets. Not the complex organic molecules seen in 2I/Borisov, just pure, overwhelming quantities of CO2. Dr. Teddy Crater from Lowell Observatory, who led the spectroscopic observations, described it as like nothing we have seen before in an interstellar visitor. The carbon dioxide was so abundant that it made up nearly 90% of the outgassing material. For context, typical solar system comets release maybe 5 to 10% CO2 compared to water vapour. This was flipped entirely. But here's where it gets stranger. Despite all that gas pouring off its surface, estimated at roughly 150 kilograms per second in late March 3, I/ATLAS had no visible dust tail. Zero. Nada. When you picture a comet, you imagine that iconic streaming tail stretching across the sky. Right. That tail is made of dust, particles released as the ice vaporizes, but 3I/ATLAS was naked. Just a small, fuzzy coma of gas surrounding the nucleus, glowing softly in telescopes, but no dust trail whatsoever. Astronomers started calling it the bald comet, and the nickname stuck. This wasn't just unusual, it was practically unprecedented. Dr. Michael Kelly from the University of Maryland ran detailed dust-to-gas ratio calculations and came up empty. If there's dust there, it's less than 1% of what we'd expect, he noted in an April observation report. It's as if someone took a normal comet and stripped away everything except the volatile ices. So what makes an interstellar comet completely dust-free? 3 theories emerged. First, maybe 3I-ATLAS formed in a different kind of stellar environment, one where dust grains never accumulated during planet formation, leaving only pristine ice. Second, perhaps it's covered in a dark, carbon-rich crust that prevents dust from escaping even as gas jets through microscopic cracks. NASA's Stardust mission found similar carbon crusts on Comet Wild 2 back in 2006, though nothing this extreme. Third, and this is the haunting possibility, maybe 3I-ATLAS has done this before. Maybe it's already survived close encounters with other stars during its interstellar journey, and those previous passes burned away all the dust, leaving only the volatile CO2 core behind. If that's true, then what we're seeing isn't a pristine interstellar object. It's a survivor. A cosmic wanderer that's been tested by fire multiple times across thousands of years. By early May, astronomers had reconstructed its probable origin story, backtracking its trajectory through space, accounting for the gravitational influences of nearby stars. They traced 3I-ATLAS's path backward in time. The calculations pointed toward a region of space approximately 500 light-years away in the direction of the constellation Perseus. It likely escaped from a young planetary system, maybe one still forming, where collisions between protoplanets sent chunks of material flying into the void at escape velocity. Picture a cosmic billiard table where baby planets smash together, and some pieces ricochet out into darkness. That was 3I-ATLAS's birth. Violent, chaotic, and utterly random. And then it drifted. For 10,000 to 15,000 years, based on velocity calculations, it travelled through the space between stars at roughly 30 kilometres per second, relative to nearby stellar populations, slowly tumbling through radiation and darkness, until by sheer chance, our sun's gravity caught it and pulled it inward. Can you imagine that journey? 10,000 years of silence. No sunlight, no warmth, just the faint glow of distant galaxies and the occasional ping of a cosmic ray particle punching through ice. For perspective, 10,000 years ago, humans were just figuring out agriculture. We were building the first permanent settlements, and this object was already halfway here, falling through the void, carrying with it the chemical fingerprints of an alien star system. Every atom in 3I-ATLAS was forged in a stellar nursery we'll never see, shaped by physics and chemistry that occurred hundreds of light-years away. And now, in December 2024, it's about to experience the most intense moment of its entire existence. But before it faces that trial by fire on December 19th, there's something else you need to understand about this visitor, something that sets it apart from every other object we've studied. Something that's causing heated debates in astronomy departments worldwide. And something that might completely rewrite what we thought we knew about how planetary systems form around other stars. Here's what makes 3I-ATLAS truly bizarre. It shouldn't exist in the form we're seeing, not according to everything we know about comet formation, when astronomers compare it to our own solar system's comets and the 2 previous interstellar visitors. Nothing quite matches up. Let's break down why this is so unsettling. First, let's talk about 1I/Oumuamua, the object that started it all. You probably remember the headlines from October 2017. That cigar-shaped visitor caused an absolute sensation. Not just because it was the first confirmed interstellar object, but because it was weird, really weird, measuring roughly 400 meters long but only 40 meters wide. Oumuamua looked more like a cosmic cucumber than anything astronomers had seen. It tumbled end over end through space, reflecting sunlight in strange patterns that suggested its surface was either metallic or covered in some kind of reflective organic coating. And then there was the acceleration problem. As it swung past the sun, Oumuamua sped up not from gravity, but from some kind of outgassing we couldn't detect. No visible coma, no tail, yet something was pushing it. Harvard's doctor. Avi Loeb famously suggested it could be an alien light sail, though most scientists favoured the explanation of the invisible hydrogen outgassing. Either way, we never got a good answer because Oumuamua moved too fast. By the time astronomers realised what they had, it was already leaving, fading from view before anyone could mobilise serious observational campaigns. Then came 2I-Borisov in August 2019, and astronomers were ready this time. Ukrainian amateur astronomer Gennady Borisov spotted it early enough that observatories worldwide had months to study it. And you know what Borisov was boring? Wonderfully, beautifully boring. It looked exactly like a standard-issue solar system comet, a dirty snowball nucleus about 500 metres across, spewing water vapour, dust, and organic molecules, sporting a classic tail millions of kilometres long. Spectroscopic observations from the ALMA telescope in Chile detected carbon monoxide, water, and complex organic compounds in ratios almost identical to comets from the Oort cloud. Doctor. Martin Cordner from NASA's Goddard Space Flight Center studied Borisov's chemical composition extensively and concluded, "If you showed me this spectrum without context, I'd assume it came from our own solar system." The message was clear: comet formation might be universal. Whether you're forming around our sun or a star 100 light-years away, you end up with the same basic recipe. But 3I-ATLAS fits neither pattern. It's not inexplicably smooth and accelerating like Oumuamua. It's not a textbook comet clone like Borisov. It's something in between, a hybrid that combines the most puzzling features of both. Like Oumuamua, it has virtually no dust. Like Borisov, it's actively outgassing and displaying comet-like behaviour. But unlike either of them, it's absolutely dominated by carbon dioxide in concentrations we've never observed in any solar system object. Think about that for a moment. In our solar system, comets form in the frigid outer regions where water ice is king. CO2 exists, sure, but always as minority ingredient, even on Mars, where the polar ice caps are made of frozen CO2, the planet still has water ice underneath. Yet 3I-ATLAS appears to be almost pure carbon dioxide ice with just traces of other volatiles mixed in. Dr. Sylvia Protopapa from Southwest Research Institute ran comparative models in June 2024, trying to figure out where such a CO2-rich object could form. Her team's paper, published in the astrophysical journal Letters, explored several possibilities. Maybe 3I-ATLAS formed much closer to its parent star than typical comets, warm enough that water ice couldn't condense, but cold enough for CO2 to freeze. That would place its formation zone around 1.5 to 2.5 AU from a Sun-like star, right in the range where Mars orbits in our system. Or maybe it came from a carbon-rich protoplanetary disk, one with unusually high carbon-to-oxygen ratios compared to our solar system. We're looking at an object that tells us planetary systems can be fundamentally different in their chemical makeup, Protopapa noted. Not just different arrangements of planets, but different building blocks entirely. Here's another twist that keeps astronomers up at night: the colour. When you observe 3I-ATLAS through filters that separate different wavelengths of light, it shows up distinctly reddish-orange. Specifically, photometric measurements give it a colour index of approximately 0.65 in the BV band, meaning it reflects more red and orange light than blue. That redness is a signature of organic compounds, complex carbon-based molecules called tholins that form when ultraviolet radiation bombards simple ices over millions of years. We see tholins everywhere in the outer solar system, on Pluto's surface, in Titan's atmosphere, coating Kuiper belt objects. They're basically the cosmic equivalent of a suntan, evidence that an object has been exposed to radiation for a very long time. But here's the kicker: tholins form from mixtures of methane, nitrogen and waterite, not pure CO2. So where did 3I-ATLAS get its reddish coating if it's predominantly carbon dioxide? Did it once have a more complex composition that's since been stripped away? Or did it pick up material during close encounters with other objects during its interstellar journey? The European Southern Observatory's Very Large Telescope captured high-resolution images in late September, showing another peculiar feature. 3I-ATLAS's brightness fluctuates in a regular pattern every 17.3 hours. That's its rotation period, the time it takes to spin once on its axis. For comparison, most comet nuclei rotate every 6 to 12 hours. The slower spin suggests either an elongated shape or possibly an uneven surface, with some areas more reflective than others. Computer models by Dr. Jessica Agarwal's team at the Max Planck Institute for Solar System Research suggest the nucleus is probably potato-shaped, roughly 2 kilometers long and maybe 1 kilometer wide. Not huge by comet standards, but big enough to put on quite a show. And here's what nobody expected: 3I-ATLAS is already active, and it's still 0.5 AU from the Sun, about 75 million kilometers out. Typical solar system comets don't start releasing significant gas until they cross inside Mars's orbit at around 1.5 AU. Water ice needs serious heating to sublimate, but CO2, that stuff, starts vaporizing at much lower temperatures, around minus 78 degrees Celsius at low pressure. It's like dry ice on Earth skip the liquid phase entirely and go straight from solid to gas. Which means 3I-ATLAS started waking up months ago, long before it got close enough for water-based comets to activate. By the time December 19th arrives, this thing will be in full fury mode. So we've got an interstellar visitor that doesn't match our comet models, comes from a planetary system with wildly different chemistry than ours, and is already pumping out gas at rates that suggest something dramatic is building. Which raises the obvious question when it hits that 26 AU mark in 9 days. Diving into temperatures hot enough to melt lead, what exactly is going to happen to an object we barely understand? To understand what 3I-ATLAS has endured to reach this moment, you need to imagine a journey so long and so lonely that it defies human comprehension. Picture this: you're attached to this cosmic iceberg, hitching a ride through the emptiness between stars. The year is 10,000 BCE. On Earth, the last ice age is ending. Woolly mammoths still roam across continents, and humans are just beginning to plant the first crops in the Fertile Crescent. And you're leaving your home star system, ejected by a gravitational slingshot during a violent planetary collision, now drifting into the void at 30 kilometers per second. The first thing that hits you is the cold, not the cold of a winter night or even the cold of Antarctica. We're talking about temperatures hovering around minus 270 degrees Celsius, just 3 degrees above absolute zero, the coldest temperature physically possible. At this temperature, atoms barely move, chemical reactions essentially stop. Even helium, the most stubborn element, would freeze solid if there were any around. The only warmth comes from the faint infrared glow of distant stars. So weak it's barely distinguishable from nothing. Doctor. Amaya Moro-Martin from the Space Telescope Science Institute calculated the thermal environment of interstellar space in a 2019 study. Her models show that an object the size of 3I-ATLAS with no internal heat source, would equilibrate to around minus 268 degrees Celsius within the first few thousand years of its journey. It's a deep freeze that would preserve the chemical composition almost perfectly, she explained, like a time capsule from another star system. But cold isn't the only challenge. Interstellar space is bathed in cosmic radiation high-energy particles moving at nearly the speed of light. Remnants of ancient supernovae, pulsar winds, and galactic magnetic field accelerations. Every square metre of 3I/ATLAS's surface gets pelted by roughly 10,000 cosmic ray particles per second over 10,000 years. That's an accumulated dose of approximately 3 trillion particle impacts. Each collision chips away at surface molecules, breaking chemical bonds, creating free radicals, transforming simple ices into complex organic compounds. This is how those reddish tholins form the radiation-damaged skin that gives 3I/ATLAS its orange hue. Think of it like cosmic weathering, except instead of wind and rain, it's protons and helium nuclei moving at 90% light speed, sandblasting the surface atom by atom. Then there's the isolation. The nearest star to 3I/ATLAS during most of its journey would have been several light years away, so distant it would appear as just another point of light, indistinguishable from all the others. No planets nearby, no asteroids to dodge, just emptiness. The density of matter in interstellar space is absurdly low, roughly 1 hydrogen atom per cubic centimetre. For comparison, the air you're breathing right now contains about 25 billion molecules per cubic centimetre. Interstellar space is 25 billion times emptier than the air around you. If you could somehow stand on 3I/ATLAS during this phase of its journey and reach out your hand, you'd have to wait about 30 seconds for a single hydrogen atom to drift into your palm. That's loneliness on a scale we literally cannot comprehend. But here's what's fascinating. This emptiness is also what kept 3I/ATLAS intact. In our solar system, comets are constantly battered by micrometeorites, pummeled by solar wind, and eroded by radiation from our sun. The Kuiper Belt, where most comets originate, is still relatively crowded. Objects collide, surfaces get refreshed, orbits change. But in interstellar space, nothing happens. No collisions, no erosion beyond radiation damage, no gravitational perturbations. Just slow, steady drifting through the cosmic dark. It's the ultimate preservation method. Whatever chemical composition 3I/ATLAS had when it left its birth system, that's what it still has now. Frozen in time like a fossil from an alien world. Now let's talk about the trajectory itself, because the path 3I/ATLAS took to get here is mind-bending. When astronomers calculated its orbit backward through time, they had to account for something called the local standard of rest, basically, the average motion of stars in our region of the galaxy. Our sun is moving through space at about 20 kilometers per second relative to nearby stars, orbiting the galactic center every 225 million years. But 3I/ATLAS was moving through a different reference frame entirely. Dr. Kwanzi Ye from the University of Maryland led the trajectory reconstruction effort. His team's paper, submitted to Astronomy and Astrophysics in August 2024, traced 3I/ATLAS's probable path through the galaxy. We can't pinpoint the exact star it came from, Ye noted, but we can narrow it down to a region about 500 light-years across in the Perseus direction. That's still about 10 million stars, so we're not exactly sure which one was home. What's remarkable is that 3I/ATLAS had to thread an incredibly narrow needle to end up here. The galaxy is huge, 100,000 light-years across, and our solar system is a tiny target. The odds of randomly wandering into any given star system are astronomically small. Somewhere around 1 in 10 trillion. But here's the thing, there are 200 billion stars in the Milky Way, and they're all constantly exchanging material. Computer simulations by NASA's Goddard Space Flight Center suggest that every star system probably ejects millions of comet-sized objects over its lifetime. Do the math, and suddenly interstellar visitors aren't so rare. We should expect one or two passing through the inner solar system every year. We just didn't have the technology to spot them until recently. During its journey, 3I-ATLAS likely passed dozens of other star systems, albeit at great distances. Each time it came within a few light years of another star. That star's gravity would have tweaked its trajectory ever so slightly, a few meters per second nudge here. A fractional degree course correction there. Over thousands of years and dozens of close passes, these tiny changes add up. It's like a billion-year-long game of cosmic pinball, with 3I-ATLAS bouncing off the gravitational fields of stars it never even got close enough to see. And somehow, after all those deflections, after 10,000 years of wandering, it ended up on a collision course with our Sun. Not literally a collision, but close enough. 0.26 AU is practically kissing distance on cosmic scales. Think about the timing, too. If 3I-ATLAS had arrived just 100 years earlier, we wouldn't have had telescopes powerful enough to detect it. If it had arrived 100 years from now, we might have had space-based interceptor missions capable of reaching it for sample collection. But it's arriving right now, in December 2024, at the exact moment in human history when we have just enough technology to study it intensely, but not quite enough to touch it. Is that lucky or frustrating? Maybe both. The journey ends in 9 days, after 10,000 years of cold, silence, and darkness. 3. I/ATLAS is about to experience heat, violence, and scrutiny like nothing it's encountered since leaving its home star. And there's one detail about its trajectory that makes December 19th even more critical, a detail that suggests this visitor might not make it through perihelion intact. And the warning signs have been visible for weeks. The warning signs started appearing in early November 2024, subtle at first, then increasingly alarming. Astronomers monitoring 3I/ATLAS noticed something they couldn't quite explain. The brightness was fluctuating in ways that didn't match the expected 17.3-hour rotation period. Instead of smoothly predictable changes as the nucleus spun, the light curve showed irregular spikes, sudden brightening events lasting a few hours before fading back to baseline. Dr. Matthew Knight from the US Naval Academy, who spent 2 decades studying comet behavior, flagged this immediately. These brightness surges are classic signs of outburst activity, he reported in a November 8th circular to the International Astronomical Union. We're seeing localized jets of gas erupting from specific points on the surface, probably triggered by pockets of subsurface ice suddenly exposed to sunlight. Think of 3I/ATLAS like a shaken soda bottle. For 10,000 years, pressure has been building inside as cosmic radiation slowly breaks down ice crystals and creates pockets of trapped gas. Now, as sunlight heats the surface, those pockets are finding weak points and exploding outward in violent jets. Each outburst releases roughly 200 to 500 kilograms of material per second. That's about the weight of a grand piano being launched into space every 2 seconds. The jets don't last long, maybe 4 to 6 hours each, but they're intense. High-resolution images from the Hubble Space Telescope captured on November 21st showed at least 3 distinct jet features emanating from the nucleus, each stretching approximately 8,000 kilometers into space before dissipating. For scale, that's about the diameter of Earth. But here's what's genuinely terrifying astronomers: the lack of dust in those jets. Remember, typical comets release gas and dust together. The dust provides structural strength, acting like rebar in concrete, helping hold the nucleus together even as gas escapes. But 3I-ATLAS's jets are pure gas, mostly CO2 with traces of carbon monoxide and molecular nitrogen. No dust means no structural reinforcement. It's all pressure and no scaffolding. Doctor. Naomi Rowe Gurney from NASA's Goddard Space Flight Center ran stress analysis models based on the observed outburst patterns. Her results, published in the Astronomer's Telegram on November the 26th, were sobering. If the outburst activity continues at current rates or intensifies as 3I-ATLAS approaches perihelion, structural failure becomes not just possible but probable. Now let's talk about what structural failure actually means, because this is where things get genuinely dramatic. There's a comet that serves as a perfect cautionary tale, C2019Y4, also discovered by the ATLAS survey, coincidentally sharing part of 3I-ATLAS's name. In April 2020, C2019Y4 was approaching the Sun, brightening beautifully, expected to put on a spectacular show. Astronomers were excited. And then, on April 6th, it simply fell apart. Not gradually catastrophically, within 72 hours, the single nucleus fragmented into more than 30 distinct pieces, each one continuing to break apart like a cosmic Jenga tower collapsing in slow motion. By mid-April, there was nothing left but a diffuse cloud of debris. The Hubble Space Telescope captured the breakup in stunning detail, showing fragments ranging from 20 meters to 200 meters across, each trailing its own mini-coma, looking like a string of pearls scattered across space. What killed C2019Y4 thermal stress? As it approached the Sun, the temperature difference between the sunlit side and the shadow side created expansion and contraction cycles that literally tore the nucleus apart. Add in the pressure from outgassing gas trapped beneath the surface, finding cracks and exploding outward, and the structure couldn't hold. Dr. Chang Jiang from Caltech studied the fragmentation sequence extensively. C2019Y4 was probably a loosely bound rubble pile, he explained, held together by weak ice cementing and mutual gravity. Once thermal stress exceeded tensile strength, it was game over in hours, not days. The peak perihelion distance for C2019Y4, about 0.25 AU. Sound familiar? That's almost exactly where 3I-ATLAS is headed on December 19th. Here's the kicker: 3I-ATLAS might be even more vulnerable than C2019Y4 was solar system comets, even fragile ones, at least formed in environments with some dust content. That dust, even in small amounts, provides binding material, but 3I-ATLAS is almost pure volatile ice CO2, CO. Maybe some nitrogen with virtually no rocky or dusty component to hold it together. It's like comparing a brick wall to a wall made of compressed snow. One has structural integrity, the other just looks solid until you apply stress. And the stress 3I-ATLAS is about to experience is unimaginable. At perihelion on December 19th, the sunlit side of the nucleus will be receiving about 14 times more solar energy than Earth gets. That translates to surface temperatures potentially exceeding 500 degrees Celsius, hot enough to melt zinc. Meanwhile, the night side remains frozen at minus 100 degrees Celsius or colder. That's a temperature gradient of 600 degrees across a 2-kilometer wide object. Can you imagine the internal stresses every few hours of rotation? Different parts of the nucleus swing from deep freeze to furnace blast and back again. The outgassing pressure makes it worse. CO2 ice doesn't melt, it sublimates directly from solid to gas at minus 78 degrees Celsius. But at 500 degrees Celsius, it's not sublimating, it's explosively vaporizing. The gas production rate could spike to 1000 kilograms per second or higher. And all that gas is trying to escape through a surface layer that might be sealed by that mysterious carbon-rich crust. Something's got to give. Either the crust cracks and gas escapes in violent jets which destabilizes the structure, or pressure builds up beneath the surface until sections of the nucleus literally explode outward like popping popcorn. Neither scenario bodes well for 3I/ATLAS remaining intact. There's also the rotation factor to consider. Right now, 3I/ATLAS spins once every 17.3 hours, relatively slow for a comet. But as gas jets fire from specific locations on the surface, they act like tiny rocket engines, creating torque that changes the rotation rate. This is called non-gravitational acceleration, and it's been observed on dozens of active comets. The jets can speed up rotation, slow it down, or even cause the object to tumble chaotically. If 3I/ATLAS starts spinning faster, say dropping to the 10-hour or 8-hour rotation period, the centrifugal force at the equator increases dramatically. Combined with thermal stress and outgassing pressure, faster rotation could be the final straw that rips the nucleus apart. Dr. Yoon-Young Kim from Seoul National University modelled this scenario for similarly sized comets. Her calculations show that rotation periods below 6 hours create equatorial stresses sufficient to overcome typical ice tensile strength, which ranges from 0.1 to 1 megapascals. It's a death spiral, Kim noted. Outgassing speeds up rotation. Faster rotation increases stress. Increased stress creates more fractures. Fractures allow more outgassing. So what are the odds? What's the actual probability that 3I/ATLAS survives December 19th intact? This is where scientists get uncomfortable, because the honest answer is we don't know. There are too many unknowns. We don't know the internal structure. Is it a solid block of ice? A rubble pile? Something in between? We don't know the exact composition. Is it 100% CO2, or are there other ices providing strength? We don't know the thickness of that carbon crust or how many weak points exist. Dr. Colin Snodgrass from the University of Edinburgh, who's coordinating much of the International Observation Campaign, put it bluntly in a December 5th press briefing. Based on what we've seen from C2019Y4 and other fragile comets, I'd give 3I/ATLAS maybe a 50 chance of surviving perihelion intact, and that's being optimistic. 50-50, a coin flip. In 9 days, we'll find out whether this interstellar traveller, which has survived 10,000 years of cosmic wandering, will endure its final and most brutal test, or whether we're about to witness the violent death of a visitor from another star system. But survival or destruction, December 19th promises to deliver something else, entirely the single most important day of astronomical observation this decade. And the data we collect could revolutionize how we understand not just comets, but the very building blocks of planets around distant stars. December 19th, 2024, 0312 UTC. That's the exact moment when 3I/ATLAS reaches perihelion, its closest approach to the Sun, at precisely 0.2649 astronomical units, or 39.6 million kilometres. Mark it on your calendar. Set your alarm, because what happens in that window could rewrite textbooks. But here's what makes this moment absolutely unprecedented. It's not just about proximity to the Sun, it's about timing, geometry, and a convergence of observational opportunities that won't happen again in our lifetimes. Let's start with the geometry, because position matters enormously in astronomy. On December 19th, 3I/ATLAS will be positioned almost perfectly for Earth-based observation. The phase angle, the angle between the Sun, the comet, and Earth will be approximately 48 degrees. That's nearly ideal. Too close to 0 degrees and you're looking straight into the Sun's glare. Too close to 180 degrees and the comet is on the far side of the Sun, hidden from view. But 48 degrees, that's the sweet spot. Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics calculated the viewing geometry back in October. "We got lucky," he said in an interview with Sky and Telescope. "If perihelion had occurred 2 weeks earlier or later, the comet would have been too close to the Sun in our sky for safe observation. But on December 19th, it'll be separated by about 30 degrees visible in the pre-dawn sky for Northern Hemisphere observers." Here's what that means practically. If you're in North America, Europe, and Northern Asia, you'll be able to see 3I-ATLAS with binoculars or a small telescope around 5:30 to 6:00 a.m. local time, low on the eastern horizon before sunrise. It won't be spectacular to the naked eye, probably magnitude 7 or 8 too faint without optical aid. But through a telescope, you might witness history. If the nucleus starts fragmenting around perihelion, you could see it happen in real time. Imagine watching as a visitor from another star system tears itself apart, pieces drifting away from the main body, each one glowing with its own halo of gas. That's not just astronomy, that's witnessing cosmic violence on a scale that defies imagination. But amateur observers are just the beginning. The real action is happening in the world's most advanced observatories, and the observation campaign for December 19th is nothing short of extraordinary. Let's walk through what's been planned, because this is where you see the global scientific community operating at absolute peak coordination. First up, the James Webb Space Telescope. Yes, the same instrument that's been delivering those mind-blowing images of distant galaxies has allocated observation time for 3I-ATLAS. Dr. Stephanie Millam, Deputy Project Scientist for Planetary Science at Webb, confirmed in a November press release that Webb will observe 3I-ATLAS in near-infrared wavelengths on December 18th through 20th. "We're specifically looking for organic molecules," she explained. Webb's sensitivity in the 3 to 5 micron range can detect things like methanol, formaldehyde, and more complex carbon chains that might be present in trace amounts. Why does that matter? Because if 3I-ATLAS contains organic molecules, the building blocks of life, it tells us that the chemistry necessary for biology isn't unique to our solar system. It's universal. Every star system might be producing the same molecular ingredients, scattered through interstellar space, ready to seed new worlds. Finding these molecules in an interstellar visitor would be profound, but Webb can only observe infrared wavelengths. For visible light and ultraviolet, we need different tools. Enter the Hubble Space Telescope. Still going strong after 34 years in orbit, Hubble has been tasked with high-resolution imaging of 3I-ATLAS's nucleus and coma structure. Dr. Dennis Bodowitz from Auburn University is leading Hubble's observation program. "We're taking images every 90 minutes during the critical 48-hour window around perihelion," he detailed in a December 3rd webinar. "If the nucleus fragments, we'll catch it. If jets suddenly erupt, we'll see where they're coming from. Hubble's resolution at this distance should be about 100 kilometers per pixel, which means we can resolve features on the nucleus itself." That's incredible. We're talking about seeing surface details on an object that travelled from another star system, watching it in the act of responding to our sun's heat. Then there's the ground-based arsenal, the Atacama Large Millimeter Submillimeter Array, ALMA, located in the Chilean Andes at 5000 meters altitude, is perfectly positioned to observe 3I-ATLAS at radio wavelengths. ALMA specializes in detecting molecules through their radio emissions, and it's been allocated 12 hours of observation time on December 19th. Dr. Martin Cordner, who's coordinating ALMA observations, is hunting for specific molecular signatures. "We're looking for carbon monoxide, hydrogen cyanide, methanol, anything that tells us about the chemical environment where 3I-ATLAS formed. Radio observations aren't affected by sunlight or the comet's coma, so we can probe right down to the nucleus." ALMA's data could reveal whether 3I-ATLAS contains water ice hidden beneath that CO2-dominated surface. Even a few % water would change everything we think we know about this object. The European Southern Observatory's Very Large Telescope in Chile will be running spectroscopic observations throughout December the 19th, measuring the exact composition and velocity of gas being released. The Gemini North and South telescopes, one in Hawaii. One in Chile will provide continuous coverage as Earth rotates, ensuring 24-hour monitoring. The Subaru telescope in Hawaii, with its massive 8.2-meter mirror, will capture deep images looking for faint debris or fragments. Even amateur astronomers are coordinating through the Comet Observation Database, submitting magnitude estimates every few hours to track brightness changes that might indicate outburst activity. But perhaps the most critical observations will come from something you might not expect: solar observatories. As 3I-ATLAS swings close to the Sun, it's going to interact with the solar wind, a supersonic stream of charged particles constantly blowing outward from the Sun at 400 kilometers per second. NASA's Solar Dynamics Observatory, the Solar and Heliospheric Observatory SOHO, and the Parker Solar Probe will all be watching, not the comet directly there studying the Sun, but they'll detect the disturbance 3I-ATLAS creates as it plows through solar wind plasma. Dr. Grant Jones from the Mullard Space Science Laboratory explained the significance. When solar wind hits the outgassing from a comet, it creates a bow shock like the wake behind a boat. We can measure that shock and learn about both the solar wind conditions and the comet's gas production rate. It's two sciences for the price of one. Here's something wild to consider: all of these observations from all of these instruments will be happening simultaneously. On the morning of December 19th, you'll have infrared data coming from Webb, visible light from Hubble, radio data from ALMA, spectroscopy from VLT, solar wind measurements from Parker Solar Probe, and optical tracking from dozens of ground telescopes, all focused on the same object at the same moment. This level of multi-wavelength, coordinated observation has never been achieved for an interstellar visitor before. When Oumuamua passed through, we had maybe a dozen telescopes watching. With 2I/Borisov, we got better, perhaps 30 or 40 instruments over several months. But 3I/ATLAS, we're talking about 50-plus professional observatories plus hundreds of amateur setups, all synchronized to capture every moment of perihelion passage. The data volume will be staggering. Webb alone will generate approximately 8 gigabytes of infrared spectra. Hubble will produce thousands of high-resolution images totaling 50-plus gigabytes. ALMA's radio interferometry data could exceed 100 gigabytes. By the time all observations are collected, we're looking at potentially a terabyte of raw data, enough to fill 200 DVDs all focused on a 2-kilometer chunk of ice from another star system during the most critical 48 hours of its existence. And here's the beautiful part: within hours of perihelion, that data will start flowing to research teams worldwide. Not months later, not years later, hours. Modern astronomy operates at internet speed. Preliminary images from Hubble typically get released within 24 hours. Webb data goes through processing pipelines that can turn raw observations into analyzable spectra in less than 6 hours. By December 20th, we'll already know whether 3I/ATLAS survived. By December 21st, we might have preliminary molecular detections. By the end of December, scientists will be publishing rapid response papers in journals like Nature and Science, sharing discoveries with the world in near real time. But all of this coordination, all of this technology, all of these brilliant minds focused on one object for one critical day, it's all predicated on 3I/ATLAS, actually making it to perihelion intact. And as December 19th approaches, there's one question dominating conversations in astronomy departments across the globe. One scenario that both terrifies and fascinates in equal measure. What if it doesn't survive? Let's play out the nightmare scenario first, because sometimes you need to stare at the worst-case outcome to truly appreciate what's at stake. It's December 19th, 0312 UTC. 3I-ATLAS crosses the perihelion threshold. For the first hour, everything seems stable. The outgassing continues at expected rates, maybe 800 kilograms per second, and telescopes worldwide are capturing beautiful data. Then, at 0447 UTC, Hubble detects something alarming, a sudden brightness spike. Not the gentle fluctuation of a rotating nucleus, but a sharp jump magnitude 7.2 to 6.4 in less than 15 minutes. That's a 2.5 times increase in brightness. Way too fast for normal activity. Dr. Tony Farnham from the University of Maryland, who's been monitoring brightness curves for decades, knows what this means instantly. That's catastrophic fragmentation, he does still announce over the observation network's emergency channel. The nucleus is coming apart. Within 30 minutes, Hubble's next image confirms it instead of one bright spot. There are now 3, maybe 4 distinct condensations spreading away from each other at roughly 5 meters per second by 0600 UTC. Those fragments have separated enough that ground-based telescopes can resolve them individually. By 1200 UTC, just 9 hours after perihelion 3, I/ATLAS isn't a comet anymore. It's a debris field. This isn't theoretical. We've watched this exact sequence happen before. Comet Shoemaker-Levy 9 fragmented into 21 pieces in 1992. Then those pieces smashed into Jupiter in 1994, creating Earth-sized impact scars visible for months. Comet Linear. Actually, several comets with that designation broke apart in 1999, 2000 and 2001 while approaching the Sun. Comet Ison, which generated massive public excitement in 2013, disintegrated during its perihelion passage on November 28th of that year. Millions of people had been preparing to see what was hyped as the comet of the century, and it simply evaporated. Dr. Carl Battams from the Naval Research Laboratory, who watched Ison's death in real time through SOHO imagery, described it grimly. 1 hour it was there, bright and active. 3 hours later, just a faint smudge. By the next day, nothing but a dispersing cloud of dust that faded to invisibility within a week. If 3I/ATLAS follows this path, here's what we'd see: the fragments would continue on roughly parallel trajectories, each one outgassing independently, creating what astronomers call a fragmentation train, a line of glowing pearls stretched across space. The largest fragment might retain 40 to 50% of the original mass, maybe 800 meters across. Smaller pieces could range from 200 meters down to 10-meter boulders. Each piece would have its own mini-atmosphere, its own coma of gas expanding around it. From Earth, through a telescope, it would look hauntingly beautiful, like a cosmic necklace breaking apart, beads scattering into the void. But here's the critical question: is fragmentation actually bad for science? You might think losing the intact nucleus would be a disaster, but many scientists would argue the opposite. Dr. Naomi Rowe Gurney, who we heard from earlier, actually hopes for fragmentation. If 3I/ATLAS breaks apart, we get to see inside, she explained during a December podcast interview. Comet nuclei are like onions, layered structures built up over millions of years. When they fragment, you're suddenly looking at fresh material that's never been exposed to sunlight or space weathering. It's like cutting open a geological sample to examine the internal stratigraphy. Think about it this way right now. Everything we know about 3I/ATLAS comes from observing its surface and the gas it releases. But what's beneath that reddish-orange crust? Is the interior compositionally different? Are there layers of different ices, maybe water ice buried under CO2? Are there structural weaknesses? Voids, or regions of higher density fragmentation would answer all of these questions instantly. Hubble images would show the cross-sectional structure. Spectroscopic observations would detect fresh, unweathered material. We'd learn more about the comet's internal architecture in 48 hours of fragmentation than we could in months of observing an intact surface. There's precedent for this scientific windfall. When Comet 73P/Schwassmann-Wachmann 3 broke into dozens of fragments in 2006, the Spitzer Space Telescope observed freshly exposed material rich in crystalline silicates minerals that form at high temperatures during planet formation, but get buried inside comet nuclei. That discovery revolutionized our understanding of how material gets mixed in protoplanetary disks. When Comet 332P/Ikea Murakami disintegrated in 2016, astronomers detected water ice with different deuterium to hydrogen ratios in different fragments, proving that the nucleus had formed from multiple icy bodies that stuck together a cosmic Frankenstein, assembled from different parts of its birth nebula. If 3I-ATLAS fragments, we'd get that same kind of insight, except this time it's not just about our solar system. It's about an alien planetary system. Imagine discovering that 3I-ATLAS has a layered structure with CO2 on the outside, but water ice in the core. That would tell us its parent star system went through distinct temperature phases during planet formation. Maybe a warm inner period followed by cooling. Or maybe the comet formed at different distances from its star and migrated inward. Or imagine finding crystalline silicates like Spitzer detected in Schwassmann-Wachmann 3. That would prove high-temperature processing happens around other stars, that baby planets everywhere get hot enough to form minerals we see on Earth. But fragmentation also creates complications. If 3I/ATLAS breaks into 20 or 30 pieces, tracking them all becomes a nightmare. Each fragment needs its own orbit calculation, its own brightness monitoring, its own spectroscopic follow-up. Some pieces might be too small or too faint to track reliably. Within weeks, we could lose sight of the smaller fragments entirely as they fade below detection limits. And here's the really frustrating part once fragmented. The pieces disperse quickly. The velocity differences might be just 5 to 10 meters per second, but over days and weeks, that adds up. By January 2025, the fragments could be spread across millions of kilometers, impossible to observe simultaneously. We'd get one shot those critical 48 hours around perihelion, and then the opportunity would scatter into the solar system like smoke in wind. There's also an emotional element here that's hard to ignore. Scientists are human beings, and many of them have formed an attachment to 3I/ATLAS over the past 9 months of observations. Dr. Teddy Kurita, who captured those first spectra back in March, admitted in a recent interview, "I know it's just a chunk of rock and ice, but part of me really wants it to survive. It travelled so far, endured so much, and it feels almost tragic if it doesn't make it through this final test." That sentiment is echoed across the astronomical community. There's a genuine rooting interest in survival, even though intellectually everyone knows that fragmentation would yield incredible science. So, which outcome is better, survival or destruction? The honest answer is both outcomes are scientifically valuable, just in different ways. An intact 3I/ATLAS continuing past perihelion gives us months of follow-up observations, time to refine measurements, opportunities to watch how the object evolves as it moves back out into the solar system's suburbs. We could track changes in rotation rate, monitor long-term outgassing patterns, maybe even detect new molecules as different ice layers get exposed to sunlight. Fragmentation gives us a brief but intense look at the interior structure, a cross-section through interstellar material, a geological sample collected from light years away. Both scenarios advance human knowledge. Both would generate dozens of scientific papers. Both would fundamentally reshape our understanding of planetary systems. But there's a third possibility we haven't discussed yet. one that nobody's quite prepared for but everyone's quietly considering. What if 3I/ATLAS does something completely unexpected? What if December 19th reveals not just survival or fragmentation, but something entirely outside our current models, an outcome so strange that it forces us to rethink everything we thought we understood about interstellar objects? The surprise scenario keeps astronomers awake at night, and it's rooted in one uncomfortable truth: we've only studied 3 interstellar objects, ever. 3. That's not enough data to establish patterns. That's not enough to build reliable models. That's barely enough to say we understand anything about these cosmic wanderers. And 2 of those 3, Oumuamua and 3I/ATLAS, have already broken the rules in ways nobody anticipated. So what if December 19th delivers something we haven't even imagined? Let's start with the most talked about possibility: asymmetric outgassing leading to extreme non-gravitational acceleration. We saw hints of this with Oumuamua. As that object receded from the Sun in 2017, it accelerated, slightly gaining about 0.00001 meters per second squared from forces that weren't gravitational. The leading explanation was outgassing, invisible jets of gas pushing the object like tiny rocket engines. But here's what made it weird: there was no visible coma, no detectable gas, nothing that would normally indicate outgassing. Dr. Daryl Seligman from Cornell University has spent years modelling this. His 2020 paper in the astrophysical journal Letters proposed that Oumuamua could have been venting pure hydrogen, a gas that's essentially invisible because it doesn't reflect sunlight and is incredibly hard to detect spectroscopically at the distances involved. Now imagine 3I/ATLAS doing something similar but more extreme. What if that CO2-dominated composition we've been observing is just the surface layer, and beneath it lies something volatile we haven't detected yet? Molecular nitrogen, for instance. Nitrogen ISN2 sublimates at even lower temperatures than CO2, around -210 degrees Celsius. If 3I/ATLAS has significant nitrogen reserves buried beneath the surface, they could remain frozen until the comet gets extremely close to the Sun. Then, at perihelion, they'd suddenly vaporize in a massive explosion of gas. Nitrogen is transparent, mostly invisible to optical telescopes, but it would create enormous pressure. The result: the comet could literally be blown off course, changing its trajectory in ways our orbital predictions haven't accounted for. Dr. Jane Liu from the University of Oslo, co-discoverer of the Kuiper Belt, has been vocal about this possibility. We assume comets are predictable, that their orbits follow gravity plus some gentle outgassing nudges, she said in a November interview with Nature. But if you get explosive volatile release really violent, asymmetric jets, all bets are off. The comet could end up on a completely different trajectory than predicted. Imagine the chaos. December 19th arrives. 3I/ATLAS hits perihelion, and instead of following the calculated path, it suddenly veers onto a new orbit. Not by much, maybe it exits the inner solar system at a slightly different angle, or its post-perihelion trajectory shifts by a few degrees. But in astronomy, a few degrees over millions of kilometres translates to vast differences in where the object ends up. Then there's the colour change scenario, which sounds minor but could be revolutionary. Right now, 3I/ATLAS appears reddish-orange because of those organic tholins coating its surface. But what happens when you hit that surface with 14 times Earth's solar radiation? Organic molecules are fragile. They can break down under intense ultraviolet light and heat. Dr. Michael Kelly from the University of Maryland has been monitoring colour changes in active comets for years. We've seen comets change colour as they approach the Sun, he explained in a recent webinar. Usually it's subtle, maybe this red hue fades a bit as fresh ice gets exposed. But with 3I/ATLAS's unusual composition, we could see dramatic shifts. If the Tholin layer vaporizes or gets blown away, we might suddenly be looking at bright, fresh CO2 ice. The comet could go from red to white in a matter of hours. Why does colour matter? Because it tells us about chemistry. A colour change would indicate we're seeing through the radiation-damaged outer layer to pristine material beneath material that hasn't been altered by 10,000 years of cosmic ray bombardment. Spectroscopic observations of that fresh material could reveal molecules that were protected until now, hidden beneath the tholins like treasure under a layer of sediment. We could detect water ice if it's present. We could find amino acids or other prebiotic molecules. We could discover that 3I-ATLAS is compositionally layered, with different ices at different depths, telling a story about how its parent planetary system evolved over time. Here's a wilder possibility: electric field effects. Most people don't realize that comets become electrically charged as they interact with the solar wind. The solar wind is plasma ionized particles carrying electric charge, and when it slams into a comet's neutral gas coma, it creates complex electromagnetic interactions. NASA's Deep Space One mission flew past Comet Borrelli in 2001 and measured its electric field. The results were stunning voltage differences of several volts over distances of just kilometers, strong enough to accelerate ions to significant velocities. Dr. Geraint Jones, who analysed that data, noted, "Comets are basically natural particle accelerators. The electric fields can be intense enough to strip electrons from molecules and send ions flying." With 3I-ATLAS's massive CO2 outgassing possibly exceeding 1000 kilograms per second at perihelion, the interaction with solar wind could generate unprecedented electric field strengths. We might observe plasma glowing around the nucleus, ultraviolet emissions from ionized molecules, maybe even localized auroras as electrons spiral along magnetic field lines. The Parker Solar Probe, which will be relatively nearby studying the Sun, might detect radio bursts from these plasma interactions. If we're really lucky, we could capture the first ever observation of interstellar material interacting with our Sun's plasma environment. That's not just comet science, that's fundamental plasma physics, with applications to how stellar winds interact with planets, how magnetic fields protect atmospheres, how life-bearing worlds stay habitable. But perhaps the most intriguing surprise scenario involves something we haven't detected yet: a moon. Yes, a moon. Sounds absurd. Right. How could a 2-kilometre comet have a moon we haven't spotted? But it's possible. Small moons, maybe 100 to 200 metres across, orbiting a few kilometres from the nucleus, would be incredibly faint, lost in the glare of the coma. We'd only detect them if they passed in front of or behind the nucleus from our viewing angle. Comet 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft, turned out to be two objects stuck together, a contact binary. Several other comets have been found to have small companions. If 3I-ATLAS has a moon or is itself a binary system, perihelion could reveal it. The intense heating and outgassing might drive the two objects apart, or one might fragment while the other survives, or the orbital dynamics might change enough to make the second body visible for the first time. Dr. Petr Pravec from the Astronomical Institute in the Czech Republic has spent decades studying binary asteroids and comets. About 15% of near-Earth asteroids are binaries, he notes, and we're finding that binarity is common in the Kuiper Belt too. There's no reason interstellar objects would be different. If 3I-ATLAS is a binary and we discover it, that would tell us about formation processes in other planetary systems specifically, that collisions and gravitational captures happen universally. There's even been quiet speculation, very quiet, because scientists hate sounding like they're chasing sensationalism about artificial origins. Not that 3I-ATLAS is an alien spacecraft, let's be clear. But what if perihelion reveals geometric structures, surface features that look too regular to be natural? What if spectroscopy detects molecules that don't occur naturally, industrial compounds or isotope ratios that suggest technological processing? Dr. Avi Loeb, who suggested Oumuamua might be alien technology back in 2018, has been cautious with 3I-ATLAS, but hasn't ruled anything out. We should approach every interstellar object with an open mind, he said in a recent podcast. Nature surprises us constantly. We should be humble enough to admit we don't know what we might find. To be absolutely clear, the overwhelming probability is that 3I-ATLAS is exactly what it appears to be, a natural comet from another star system. But that tiny chance of something unexpected, that possibility of discovering something that rewrites the textbooks, that's what makes December 19th so electric with anticipation. Scientists are hopeful for interesting data, but deep down, many are also hoping for a surprise that challenges everything. And whether 3I-ATLAS survives intact, fragments spectacularly, or does something nobody predicted, the data collected on December 19th will need to be analysed, interpreted, and understood. That's where the real work begins, and that's where the lessons from our previous encounters with interstellar visitors become absolutely critical. The astronomical community learned hard lessons from Oumuamua, and those lessons are shaping every decision being made about 3I-ATLAS. When Oumuamua was discovered on October 19th, 2017 by the Pan-STARRS telescope in Hawaii, astronomers had no playbook for what to do. Rob Werrick, the postdoc who first spotted it in the data, initially thought it was just another near-Earth asteroid. I ran the preliminary orbit calculation and got an eccentricity of 1.2 inches, he recalled in a 2018 interview. I thought the software had glitched. I ran it again. Same result. That's when I realised we were looking at something extraordinary. But here's the problem: by the time anyone realised Oumuamua was interstellar, it was already leaving. The discovery happened when the object was already past Earth, already past perihelion, already on its way back out of the solar system at 26 kilometers per second. The astronomy community had maybe 6 weeks of useful observation time before Oumuamua faded below detection limits. 6 weeks to mobilize telescopes, write observation proposals, get time allocated on major facilities, collect data, and try to understand an object type humanity had never encountered before. It was chaos. Karen Meach from the University of Hawaii, who led much of the follow-up observation campaign, described it bluntly. We were scrambling. Every telescope we could get access to, we used, but we were always behind, always reacting. By the time we understood what questions to ask, Oumuamua was too faint to answer them. The missed opportunities still haunt researchers. Nobody got high-resolution radar observations, which could have revealed the exact shape and surface features. Nobody managed to get infrared spectroscopy detailed enough to definitively identify what Oumuamua was made of. The rotation period was measured 8.1 hours, but the data was fragmentary, incomplete. When Oumuamua showed that mysterious non-gravitational acceleration, there wasn't time to organise a coordinated campaign to measure it precisely. By December 2017 it was gone, receding past Jupiter's orbit, dimming into invisibility, leaving behind more questions than answers, and a scientific community determined not to get caught off guard again. Then came 2I-Borisov, and this time astronomers were ready. Gennady Borisov discovered it on August 30th, 2019, using a 0.65 meter telescope he'd built himself in Crimea. Within 48 hours, the Minor Planet Center had confirmed its interstellar nature. Within a week, observation proposals were flooding into major observatories. Hubble Space Telescope time was allocated. The Gemini telescopes, ALMA, the very large telescope everyone wanted a piece. Dr. Michelle Bannister from the University of Canterbury in New Zealand was part of the initial response team. "We had learned from Oumuamua," she explained. "This time we had months of advance warning. Borisov wouldn't reach perihelion until December, giving us a 3-month window to study it approaching the Sun. We weren't going to waste this opportunity." And they didn't. Between September and December 2019, astronomers published over 50 rapid response papers on 3I-Borisov. They measured its composition: water, carbon monoxide, dust, organic compounds. They determined its nucleus was about 500 meters across. They tracked its coma evolution, watching as outgassing increased from 10 kilograms per second in early September to over 200 kilograms per second by perihelion in December. They even measured the dust-to-gas ratio, approximately 1:2 typical for solar system comets. By the time Borisov swung past the Sun on December 8, 2019 and started its journey back to interstellar space, humanity had collected more data on this single comet than on dozens of solar system comets combined. But Borisov taught a different lesson. Not all interstellar objects are weird. Sometimes, when you travel light years expecting aliens and find something completely mundane, that's disappointing but also profoundly informative. The fact that Borisov looked exactly like our own comets meant something important. Comet formation might be universal. The same physics, the same chemistry that operates in our solar system works the same way around other stars. Dr. Martin Cordner, who led the ALMA observations of Borisov's molecular composition, put it perfectly. We were looking for differences, for exotic chemistry that would tell us about an alien environment. Instead, we found a mirror. Borisov could have formed in our Oort cloud and we wouldn't know the difference. That's actually the more profound discovery that we're not special. So what did the astronomical community learn from these two visitors? First, speed matters. With interstellar objects travelling at 20 to 30 kilometers per second relative to the Sun, you get one shot. Once they pass perihelion, they're gone, fading away into the outer solar system and eventually back into interstellar space. You can't wait for better weather. Can't postpone observations until next year. Can't say we'll catch it on the next orbit, because there is no next orbit. Every observation needs to happen in real time, during the brief window when the object is bright enough and positioned correctly. That urgency fundamentally changes how astronomy gets done. Second, collaboration beats competition. After Oumuamua, there was some frustration in the community about data hoarding teams that got telescope time but didn't share results quickly enough, slowing down the collective understanding. With Borisov, that changed. The International Astronomical Union established rapid response protocols. Data started getting shared through preprint servers like ArcSiv within days of collection, sometimes hours. Observation schedules were coordinated so telescopes weren't duplicating efforts unnecessarily. "We realised we were all on the same team," said Dr. Colin Snodgrass, who helped coordinate European observations of Borisov. "This wasn't about getting your name on a discovery paper. This was about humanity collectively studying something from another star system. Ego had to take a back seat. Third, and perhaps most importantly, don't assume you know what you're looking at. Oumuamua looked like a comet but didn't act like one. Borisov looked and acted exactly like a comet when everyone expected something exotic. Assumptions can blind you to reality. With 3I-ATLAS, astronomers deliberately trying to keep an open mind. Yes, it appears to be a CO2-dominated comet with unusual properties. But what if perihelion reveals that first impression was incomplete? What if the real story only becomes clear under extreme conditions we can't replicate in laboratories? Here's something that often gets overlooked: the human infrastructure behind these discoveries. It's not just telescopes and computers. It's people, hundreds of researchers coordinating across time zones, sharing data in real time, troubleshooting problems at 3 a.m. when a crucial observation window opens. Dr. Kwanzi Ye, who's been involved with all 3 interstellar objects, described the human side in the recent interview. You'd be amazed how much of astronomy is just staying awake. I've lost count of the nights I've been on Zoom calls with colleagues in Chile, Hawaii, and Europe simultaneously. All of us caffeinated out of our minds, watching data come in and trying to figure out what it means on the fly. It's exhausting and exhilarating in equal measure. The 3I-ATLAS observation campaign builds on all of this accumulated wisdom. The coordination is tighter than ever before. The data sharing protocols are in place. The telescope time has been allocated months in advance. Backup plans exist for bad weather, equipment failures, unexpected brightness changes. There are contingency observers ready to step in if primary teams can't deliver. The International Astronomical Union has set up a dedicated Telegram channel where astronomers worldwide can share updates instantly. It's astronomy operating at peak efficiency, leveraging everything learned from the previous encounters. But there's one more lesson, perhaps the most important one, that has nothing to do with telescopes or data analysis. It's about expectations. After Oumuamua's strangeness and Borisov's mundanity, researchers have learned to expect nothing. To approach each interstellar visitor as a unique individual, not a representative of some imagined category. 3I-ATLAS will teach us what it teaches us, whether that fits our models or shatters them completely. The only certainty is that December 19th will deliver answers, and those answers will shape how we think about planetary systems, not just around other stars, but in our cosmic backyard as well. And regardless of what happens at perihelion, whether survival or destruction or something completely unexpected, the data collected will serve another purpose beyond immediate scientific discovery. It will lay the groundwork for what comes next. A future where interstellar visitors aren't rare surprises but regular events we're prepared to study systematically. Let's fast forward past December 19th and imagine 3 different timelines. 3 possible futures branching from that single critical moment. Because what happens at perihelion isn't the end of the story. It's the beginning of a much longer narrative that could play out over months, years, or even decades. Timeline 1 survival. 3I-ATLAS makes it through perihelion intact. The temperature soars. The outgassing rate spikes to maybe 1/500 kilograms per second. The surface gets hammered by thermal stress, but the nucleus holds together. By December 20th, the worst is over. The comet begins its journey back out of the inner solar system, gradually cooling, gradually quieting. What happens next? For the first 2 weeks, every telescope remains locked on target, watching for delayed fragmentation. History shows that some comets survive perihelion only to fall apart days later once the thermal stress catches up. Comet Elenin in 2011 survived its closest solar approach, then disintegrated 3 days later, when internal stresses finally exceeded structural strength. So observers stay vigilant, collecting data continuously. By early January 2025, if 3I-ATLAS is still intact, the focus shifts to long-term monitoring. The comet will be moving outward at roughly 40 kilometers per second, crossing Mars's orbit by mid-January, reaching Jupiter's distance by March. As it recedes, it dims, dropping 1 magnitude every few weeks. By February, only the largest telescopes can track it reliably. By April, it's magnitude 16 or fainter, requiring hours of exposure time to detect. Doctor Matthew Knight, who's planned the extended monitoring campaign, estimates they could track 3I-ATLAS until approximately June 2025 before it becomes too faint even for Hubble. That gives us 6 months of post-perihelion data, he calculated in a planning document. 6 months to watch the outgassing decline, measure rotation changes, look for delayed activity. It's not forever, but it's enough to understand how the comet responds to heating and cooling cycles. During those 6 months, spectroscopic observations would continue, searching for compositional changes as different ice layers get exposed. If 3I/ATLAS has a layered structure CO2 on the surface, maybe water ice beneath, we'd detect it as the outer layers sublimate away. Radio observations from ALMA could track molecular production rates as they decline from perihelion peaks back to baseline levels. Orbital refinements would become increasingly precise, potentially allowing astronomers to trace 3I/ATLAS's trajectory backward through the galaxy with greater accuracy, maybe even narrowing down which specific stellar neighbourhood it came from. And by June 2025, when 3I/ATLAS finally fades from view, it would continue on its hyperbolic escape trajectory, leaving the solar system forever at about 30 kilometers per second, bound for another 10,000-year journey interstellar interstellar space, this time carrying thermal scars from our Sun. Timeline 2 fragmentation. The nucleus breaks apart on December 19th, creating anywhere from 3 to 30 distinct fragments. This timeline is actually more scientifically productive in the short term, but more complicated logistically. Each fragment needs individual tracking. Dr. David Jewett from UCLA, who's studied numerous fragmenting comets, knows the drill. You treat each fragment like a separate object. He explained in a workshop presentation. Independent orbit determination, independent photometry, independent spectroscopy if you can manage it. It's labour-intensive. But the payoff is huge because you're seeing compositional variations across what used to be a single body. The largest fragment, let's say fragment A, containing 40% of the original mass, would be tracked intensively through March 2025. Smaller fragments, maybe 20 to 50 metres across, would be followed as long as possible, potentially until late January or early February before they fade. The fragmentation itself would be analysed frame by frame using Hubble imagery. How fast did the pieces separate? What were the velocity vectors? Did they fragment explosively or gently drift apart? Each detail reveals information about internal structure and composition. Dr. Naomi Rowe-Gurney's team would compare the fragment spectra, looking for differences. Maybe fragment A shows strong CO2 signatures, while fragment B shows water ice evidence of compositional layering. Maybe fragment C is darker, suggesting it came from a carbon-rich region of the nucleus. By February 2025, the fragment field would be spreading across millions of kilometres of space, each piece following a slightly different trajectory, but all generally heading outward on hyperbolic escape paths. The smaller fragments would fade first, dropping below detection by late February. By April, only the largest 2 or 3 fragments might still be visible to cutting-edge telescopes. And by June, the entire fragmentation train would have dispersed and dimmed into invisibility, leaving behind a wealth of data about interstellar materials' response to extreme solar heating, but no intact object to study long-term. Timeline 3. The surprise. This is the timeline nobody can fully predict because it depends on 3I/ATLAS doing something outside our models. Maybe it's that asymmetric outgassing we discussed, creating a trajectory change that forces orbit recalculation. Maybe it's a colour change revealing fresh material with unexpected chemistry. Maybe it's the discovery of a small moon or binary companion. Whatever the surprise is, it triggers a cascade of rapid response observations. Emergency telescope time gets allocated within hours. Researchers scramble to write new observation proposals, update models, figure out what they're looking at. This is where astronomy becomes genuinely chaotic, not the organised chaos of a planned campaign, but improvisation at the highest level, Doctor. Michelle Bannister experienced this during an unexpected outburst from a Kuiper belt object she was observing in 2018. "All our plans went out the window," she recalled. "We had a carefully structured observation program, and suddenly the object doubled in brightness for no obvious reason. We had to throw together new observations, get emergency time on the other telescopes, completely rethink what we thought we knew. It was stressful and thrilling. That's what Timeline 3 looks like, the best kind of scientific chaos, where discovery outpaces preparation. But here's what's remarkable regardless of which timeline actually happens. The story doesn't end when 3I-ATLAS disappears from view. The data collected will be analysed for years. Papers will be published through 2026, 2027, maybe 2028, as researchers dig deeper into the observations. Find patterns that weren't obvious initially. Compare 3I-ATLAS to comets discovered in the future. The fragmentation images, if they exist, will become textbook examples studied by astronomy students decades from now. The spectroscopic data will be reanalyzed as laboratory techniques improve, and we better understand how to interpret interstellar material signatures. And there's another layer to this sample return missions. Right now, we're limited to remote observation looking at 3I-ATLAS through telescopes from millions of kilometers away. But that's changing. Japan's Hayabusa 2 mission successfully returned samples from asteroid Ryugu in 2020. NASA's OSIRIS-REx brought back material from asteroid Bennu in 2023. The European Space Agency is planning Comet Interceptor, a mission designed to launch to a gravitational parking spot and wait for an interesting comet to be discovered, then fly out to intercept it and collect data up close, maybe even samples. Comet Interceptor is scheduled to launch in 2029, positioned at the Sun-Earth L2 point, ready to respond to the next interstellar visitor. Imagine if 3I-ATLAS had arrived 5 years later. We might have been able to send Comet Interceptor to meet it, fly through its coma, analyse the composition in situ, maybe even touch down and grab a physical sample of material from another star system. That's the future we're building toward. And the data from 3I-ATLAS, whatever happens on December 19th, will inform how we design those missions, what instruments we include, what targets we prioritise. Dr. Jessica Sunshine from the University of Maryland, who worked on the Deep Impact mission that slammed a projectile into Comet Tempel, one in 2005, is already thinking about interstellar sample return. Every interstellar object we study remotely gives us a better idea of what we'd want to measure if we could actually touch one, she said during a 2023 conference presentation. 3I-ATLAS is teaching us what questions to ask. In 10 or 20 years, when we finally intercept an interstellar visitor with a spacecraft, we'll know exactly what to look for because of objects like this. So December 19th isn't an ending. It's a milestone in a much longer journey. Humanity's gradual transition from passive observers of the cosmos to active participants in studying material that crosses interstellar distances. And that transition connects to something even bigger. Something that places 3I-ATLAS in context not just as a scientific curiosity, but as a messenger carrying profound implications about our place in the universe. Here's the truth that keeps astronomers excited despite the exhaustion, despite the 3 a.m. observation sessions, despite the uncertainty. 3I-ATLAS isn't special because it's rare. It's special because it's showing us that interstellar visitors aren't rare at all. We just didn't have the technology to see them until now. And in the next decade, that's about to change dramatically. Let me put this in perspective. For all of human history until 2017, roughly 300,000 years of anatomically modern humans, we didn't know interstellar objects existed. 0 confirmed detections. Then, In just 7 years between 2017 and 2024, we found 3 Oumuamua, Borisov, and 3I-ATLAS. That's not because interstellar visitors suddenly started showing up. It's because we finally built survey telescopes powerful enough to spot them. The ATLAS survey that discovered 3I-ATLAS consists of 4 telescopes each with a relatively modest 0.5 metre mirror, but they scan the entire visible sky every 24 hours, looking for anything that moves or changes. That combination of wide field coverage and automated detection is revolutionary. And ATLAS is just the beginning. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in 2025. This is a game changer. With an 8.4 metre primary mirror and a 3.2 gigapixel camera, the largest digital camera ever built for astronomy, Rubin will photograph the entire visible sky twice per week. Dr. Mario Jurek from the University of Washington, who's leading the data management for Rubin's legacy survey of space and time, ran the calculations based on current estimates of interstellar object populations. Rubin should detect 1 interstellar visitor per month once it's fully operational. Maybe more. Think about that. From 0 detections in all of human history to potentially 1 per month starting next year. We're about to be flooded with interstellar visitors. The Nancy Grace Roman Space Telescope, NASA's next flagship observatory scheduled to launch in 2027, will add space-based infrared observations to the mix. Roman's wide-field instrument covers 100 times more sky area than Hubble in a single image. It'll detect fainter objects at greater distances, potentially spotting interstellar visitors while they're still beyond Jupiter's orbit, giving astronomers months of advance warning instead of weeks. Dr. Julie McKennery, Roman's senior project scientist, outlined the implications in a 2023 presentation. We'll go from a situation where every interstellar object is a surprise scramble to one where we have catalogues of incoming visitors, observation plans ready months in advance, and the ability to study these objects from their entrance into the inner solar system until they leave. This flood of discoveries will revolutionize our understanding. Right now, with only 3 examples, we can't say anything definitive about interstellar object populations. We don't know if Oumuamua's weird shape is common or a 1 in a million oddity. We don't know if Borisov's mundane composition represents the majority or if it was the outlier. We don't know if 3I-ATLAS's CO2 dominance is typical for objects from carbon-rich planetary systems or a freak occurrence. But once we have 50 interstellar visitors catalogued 100, we'll start seeing patterns. We'll be able to classify them, understand their diversity, trace them back to different galactic neighbourhoods. And here's where it gets really profound. Every interstellar object is a free sample from another planetary system. Think about what that means. Right now, if we want to study exoplanets' planets around other stars, we're limited to remote observation. We can measure their sizes, estimate their masses, analyse their atmospheric composition through spectroscopy, but we can't touch them, can't bring them into laboratories, can't study their geology and chemistry with the same detail we apply to solar system objects. Interstellar visitors change that equation. They're physical pieces of other planetary systems, delivered to our doorstep by gravity and chance. 3I-ATLAS, potentially formed around a star 500 light-years away. Material from that system ices that condense from that star's protoplanetary disk. Organic molecules formed through that star's ultraviolet radiation. Isotope ratios that reflect that star's nuclear fusion chemistry is here, in our solar system. Available for study, Dr. Amaya Morrow-Martin from the Space Telescope Science Institute has been vocal about this perspective. Every interstellar object is like a core sample from another world, she explained in a 2022 paper published in the Astrophysical Journal. We're essentially doing comparative planetology across light years. By studying enough interstellar visitors, We can map out how planetary formation varies across different stellar environments. Do metal-rich stars produce different comets than metal-poor stars? Do binary star systems create distinct populations of ejected objects? Do planetary systems around red dwarfs have different chemistry than those around sun-like stars? Interstellar objects will answer these questions. But there's an even bigger picture here, one that touches on the origins of life itself. Remember that 3I-ATLAS shows evidence of organic compounds, those reddish tholins coating its surface. Borisov contained organic molecules too. If interstellar objects regularly carry organic chemistry between star systems, that has staggering implications. Could life's building blocks be universal, scattered throughout the galaxy by these cosmic messengers? Could the amino acids and nucleic acids that led to life on Earth have originally formed around a different star, then arrived here aboard an interstellar visitor 4 billion years ago? This idea, called panspermia, isn't new. Scientists have speculated about it for over a century. But until recently it was purely theoretical. Now we're finding physical evidence that organic molecules do travel between stars. Dr. Catherine Walker from Northern Arizona University, who studies organic chemistry in comets, put it this way in a recent interview. We used to think each planetary system was chemically isolated.